is pouring rain out there today on this lovely President's Day, where you all are at home, probably watching a movie, staying warm by the fire. And Mr. Mac is here doing extra practice videos. 5.1, we are dealing with systems of equations. So we're going to go through a bunch of different techniques on how to tell whether the ordered pair is a solution. So we have two lines here, and we have to think of them as two lines. This is a line. There are an infinite number of solutions to that problem. The most obvious are 1 and 3, 2 and 2. You can also have 0 and 4. You can have -1 and 5. So we can go on forever. And then this is a line also. And solutions to that are 1 and -1. And there are an infinite number of solutions to that. So they create a line, something like this. And then the blue equation creates a line. And that intersection is what we call the true. It is where that location, that coordinate, that point, that x and y value for that location, if we plug it into both of these equations, we get true for each of them. That's why I call it a true. So if I pick this point, it would be false. It would be false for both of those equations. This would be true, false. This point here would be false for the green, true for the blue. So when we find a solution of the system, we're looking for this point of intersection. And so it starts off by providing you a point, and you check to see if it is a solution. We're checking to see if this is true. Is it true for both equations? So we're going to take the first equation. We know that this equation is written x comma y, or that coordinate is written x comma y. We're going to take the x value, substitute it in, the y value, substitute it in, and then we're going to simplify the left side. We're not going to move things over across the equal sign. We're going to simplify the left side, simplify the right side, and we get true. So this one is true so this point is a solution to this green equation. Now we're going to take the other equation and we're going to plug in those values. And we get 6 minus 1 is 3, 5 equals 3. That is false. So we know that this point lies on this green line, but not the blue line. So if you want to see what that means, if we take those two, that means this point sits somewhere on this line, somewhere along this line, but not at the point of intersection, because it is true, so it's going to be on the green line somewhere, but it does not lie anywhere on the blue line. Cool. So that's what we're going to do with each of these problems. So first one is no, it is not a solution. I guess I should write that somewhere. That would make sense. Whoops. My answer is going to be not a solution. So that would be my final answer, reading the directions. So we're going to do this a little bit faster. We're going to plug in the coordinates and simplify. That's 8 minus 6. 6 is 2. So yes, that's true. That is on this first line. So that point is a solution to that equation. And then 3 times 4 minus 3 times -3 equal 21. That's 12 plus 9. 21 equal 21. That is true. So yes, that point, yes, what's the point? 4, -3 is a solution to the system. Good. So, very straightforward, just plugging and simplifying, knowing our orders of operations. That's going to be -6. So we get 4 equals 4. That's a solution. 8 times -1.5 plus 2 times 4 equal -4. So that's going to be -12 plus 8. -4 equals -4. That's true also. So yes, -1.54 is a solution to the system. Good, that's number 3. Number 4, now they draw those lines that I was talking about. And so we have to interpret where the point of intersection is. So we're saying, well, that wasn't very big. We're saying the point of intersection from these graphed lines. They may not be true representations of this. I don't know if this is this one. Actually, I could figure out if that's that one, which it is not. So we're making the assumption that these equations have been graphed correctly. That's sort of how this question goes, but so we don't have to worry about whether it's graphed. We're just taking their graphing for granted that they did it correctly. So this is the point 2, -2. First of all, we have to decipher how we can write a coordinate on from a coordinate plane. So that is 2 on the x, -2 on the y. So they're saying that is the point of intersection. So we're going to take each of these equations and we're going to plug in those x and y values. 6 plus 8 equal 10. 14 does not equal 10. So I don't even have to go any further. I know that that is not the point of intersection, that they graph those lines incorrectly, or those lines don't represent the equations provided. So use the graph to solve the system, check your solution. Oh, why did I plug in -4? That was interesting. I think I did the math. Sorry. That is correct. Oh, you probably were like, why did you plug in -4? What, every 10 videos, maybe every 5 videos, Mr. Mac makes a mistake like this where he writes something, he's not focusing on his work, what he's doing, he's trying to multitask. So it is a point, it is a solution to this equation. So yes, now let's try the other one. Hiya, hiya. Plus -2 equals 0. 0 does equal 0, so this is a solution. Use the graph solve, check your solution. Yes, that is graphed correctly, and it is a solution. 2, -2 is the solution to the system. Sorry. You're so good to me. You're so patient with all my silliness. Hopefully. All right, let's take that point. That point is going to be -1, -3, focusing, making sure we're writing things, noticing the increments. Increments are by 1, so we're to the left 1, down 3. So let's take the first equation. We have -1 minus 2 times -3 equal 5. -1 plus 6 equals 5. 5 definitely equals 5. So that is a solution. 2 times -1 plus -3 equals -5. That's -2 minus 3 equals -5. Negative 5 equals negative 5. So yes, the point negative 1, negative 3 is a solution to the system. Good. Number 6. Number 6 is a little bit different. Now we have to look at the equations and we have to graph them. So looking at the equations, we see that it's in slope-intercept form, so we can pull out the slope and the y-intercept. We're always going to pull out the y-intercept first, that's 3, and then we're going to use the slope, which is negative 1, which means down 1, right 1. And then we're going to make a line. No, I didn't want that. I want blue. And we're going to graph that, and we're going to extend it so we can see all of the solutions. Now, we don't like graphing so much because graphing is somewhat inaccurate, but we'll use it for the time being. Let's graph the other equation. We have a y-intercept of 5. 1, 2, 3, 4, 5. We go up 5, and then a slope of 1. Up 1, right 1, up 1, right 1. We can also go down 1, left 1 to help us, and that takes us to the point of intersection, which is nice. So we're making the assumption that that is the point of intersection, which would be negative 1, 4. And it takes, well, it doesn't say check. We should check. We're checking just for purposes. 4 equals negative 1, the opposite of negative 1 plus 3. 4 equals 1 plus 3, 4 equals 4. And we can check the other equation. 4 equals negative 1 plus 5. 4 equals 4. We're good. So that took less than 30 seconds. Same thing, we're in slope-intercept form. We love slope-intercept form. We're going to graph that equation. And we are going to go up 2 to the y-intercept. My slope is 1/2. Up 1, right 2. Up 1, right 2. Down 1, left 2 could also be the same equation. The same slope, excuse me. And we're going to connect those relatively accurately. Actually, that's not bad right there. We're going to graph this other equation, y-intercept of 4. 1, 2, 3, 4. And a slope of negative 1/2. That's down 1, right 2. Down 1, right 2. And that takes us already to our point of intersection, our solution. So we don't have to do too much. This is the nice thing about extending. Now this is where graphing does help you. This is where it is efficient, is you can manipulate the slopes to get you to that point of intersection, which is 2, 3. 2, 3, let's check it. Check 2, 3. Does 3 equal 1/2 times 2 plus 2? 3 equals 1 plus 2. 3 equals 3, yes. And does 3 equal negative 1/2 times 2 plus 4? 3 equals negative 1 plus 4. 3 equals 3. Yes, yes, that is the point of intersection. All right, one is in standard form and one is in slope-intercept form. Standard form, we are going to find the x and y intercepts. So we could use the cover-up method. If we cover up the y term, we're left with 3x equals 6. Divide both sides by 3, and we get 2. So my x-intercept is at 2. If I cover up the x term, I'm left with negative 2y equals 6. Divide both sides by negative 2, and we get y equals negative 3. So on the y-axis, we go to negative 3. We have 2 points. We can make a line, and we graph them, connect them, get somewhat. Now, this is where it gets a little bit harder. We could see that the slope is 3/2, but I don't think we have to get there. We're going to do this. Y equals negative 3. We should observe that there's only one variable, the variable y, so it's going to be either horizontal or vertical. And we know that when there's one variable, it goes through that axis. So y equals -3. It's going to go through the y-axis at -3. So at -3, and we get this line like this. It's a horizontal line, and our point of intersection looks like it's going to be right there, which is 0, -3. Let's check our answer. So we have 3 times 0 minus 2 times -3 equals 6. 0 plus 6 equals 6. 6 equals 6. And then we have -3 equals -3. And yes, that is our point of intersection, 0, -3. That has two variables. That's in slope-intercept form again. So slope-intercept form has a y-intercept of 0. There is no constant. And then we use our slope, which is up 4, right 1. Up 4, right 1. We're going to connect the dots. We also could have gone down 4. That's going to be there. So that looks a little bit like that, I think. That's sort of as close as we can get with not perfect lines. And now we have a y-intercept of 8 and a slope of -4, down 4. 1, 2, 3, 4, right 1. 1, 2, 3, 4, right 1. And we graph it, and these are working out quite nicely. We're projecting my slope into the intersection of the other line. Let's make an assumption that our point of intersection is going to be 1, 1, 2, 3, 4. 1, 4. Let's check it. We have 4 equals 4 times 1. 4 equals 4. And we have 4 equals -4 times 1 plus 8. 4 equals -4 plus 8. 4 equals 4. And you say, well, I knew it the line before. Just write it out. It takes 2 seconds. 2 seconds to check your answer, to do all the work. Just do it. Also, slope-intercept form. So they clearly like to give us these equations in slope-intercept form. We have a y-intercept of 3, a slope of 4, up 1, right 4, 1, 2, 3, 4. I'm going to go down 1, left 4, 1, 2, 3, 4, just to create that line. It does not matter which way you extrapolate the slope out. Just depends where the other line is, whether you need to continue to extrapolate. You may come back and do it in a different fashion. 5, 1, 2, 3, 4, 5 is my y-intercept. My slope is up 3, 1, 2, 3, right 4, 1, 2, 3, 4. So that's definitely in the wrong direction. Let's go down 3, 1, 2, 3, left 4, 1, 2, 3, 4. So we see that's a great example of, thank goodness I pushed that slope out in the other direction. Kind of felt it was going to be over in that general area. There's my suggested solution. Let's test it out. I am saying it's 1, 2, 3, 4, -4, 2. Let's check. So 2 equals 1/4 times -4 plus 3. 2 equals -1 plus 3. 2 equals 2, yes. Let's use the other equation, plugging in our y value, which is 2 equals 3/4 times my x value, which is -4 plus 5. 2 equals -3 plus 5. 2 equals 2. And that is the point of intersection. Number 11. A couple more here. 3 more. Solve the system by graphing, standard form. So now we go back to the cover-up method. We're going to cover, oh, hello. That's kind of ugly. Okay, so that's 7/3 is x. 7/3 is right there is 2 1/3. When we cover up the y, that is negative 1 3/4, 1 3/4, negative 1 3/4, which takes us about there. Oh, that's not going to be super attractive, but we'll see. We may have to maybe rewrite it in slope-intercept form. That might be our technique. We may have to use different ones. We may find that, you know what, this is too vague, finding the point of intersection through the intercept. So we're going to cover up that. We get x-intercept is going to be 3/5. 3/5, okay, on the x-axis. That's kind of like right there. And my y-intercept is going to be 1 1/2. So y-intercept is 1 1/2, which is about there. Let's draw the line. Can we make a assumption? Well, we could make an assumption that it's there, 1 -1. Let's try it. Let's check it out. And this is the fun part, is 1 -1. This is why we check our work. This is why when we graph, we have to check. 3 times 1 minus 4 times -1 equals 7. 3 plus 4 equals 7. 7 equals 7. So this is a solution to that blue line. And now let's try the other one. We have 5 times 1 plus 2 times -1 equals 3. 5 minus 2 equals 3. 3 equals 3. And it's a solution to this. So yes, it ended up being my point of intersection, my solution to the system. I got lucky. I love it. A test has 20 questions and is worth 100 points. The test consists of X true-false questions worth 4 points each, and Y multiple choice questions worth 8 points each. How many of each type of questions are on the test? All right, so there are 20 questions. So this 100 points is not relevant. Relevant? I don't know how to spell relevant, but it's not relevant. This is important. There are 20 questions of multiple choice questions and true and false questions. So I have X number of true and false questions. I have Y number of multiple choice questions. And I know how many total questions I have. Total questions. So if I add X plus Y, which are the number of each, or T plus M, T is the number of true and false, M is the number of multiple choice questions. If I add those up, it must equal 20. Now, if true and false are worth 4 points each, if I take 4 times the number of questions, that should give me the total number of points for true and false. And multiple choice is worth 8 points each. So if I take 8 and multiply it by M, actually, that is relevant, very relevant. That would give me 100. So this is the total points for true and false. This is the total points for 8. And if I add the total points of each of those categories, it should equal 100. Now I can take that and I can graph those on a graph to find where they intersect. So how many of each type? So we are, oh, all right, well, let's see, we're gonna go in, we gotta go to 100, no, we'll go 20, so fives, go by fives. So we'll graph this, we'll see if that works. We'll graph this one. The t-intercept is 20, so we have 10, so twos? Can we buy by twos? If I do that, that's going to be 25. No, so let's do, well, the t, sorry. let's do this. Let's see what we're dealing with. T-intercept is 20. M-intercept is also 20. T-intercept is going to be 25. M-intercept is going to be, what's that? 100 divided by 8 gives me 12.5. 12.5, that's a horrible 5. So let's make this M, let's make this T, alphabetical order. Doesn't have to be, but it usually helps. So my T-intercept is 20. Let's go. My largest number is 25. So I don't want to go by 5s. I kind of want to go, I don't want to go by 3s. So 4s? Yes, let's go by 4s. Yeah, let's do 4. That's, I don't know, 20, yeah, 4. All right, here we go. 4s. Hold to it, Mr. Mac. T-intercept is 20, so 20 would be, if we're going increments of 4, we go up 5. 1, 2, 3, 4, 5, that would be 20. And 1, 2, 3, 4, 5 would be 20 also. Sorry, it's just making sure that hopefully I'm going to get a point of intersection in increments of 4. Let's do the green one. Those are my intercepts. So T-intercept is 25. So 6 is 24. So 25 is going to be a little bit above the 6th increment. 12.5 is going to be 3 and a little bit. 1, 2, 3 and a little bit. Because 3 times 4 is 12. And we have 12.5. So this might not necessarily work, but we'll see. If, oh, yeah, that doesn't look like it's going to be. I mean, do I have to go by increments of 1? So what is that, 10? What's that, 4? So it's like 6, maybe 5. 5 on M's. So this is where you have to test and see. So that point kind of looks like 5 because that's increments of 4, maybe 6. It's like 5. What is that? M. M is either 5 or 6. And T is going to be 1, 2, 3, 4, 16. No, 16. So like 15 or 14. T is either 14 or 15. Well, that has to equal 20, so it's either going to be these two or these two. So I'm thinking about M plus T must equal 20. So I'm going to check. Both of those are going to be, both of those will work for the blue. So now I got to see which one works for the green. So I'm going to check. This is a good little exercise in how to get the solution. So if I check, I'm first going to check, it is in M comma T. My MT is my coordinate. I'm going to check, 515. MT, so 515. Let's do 4 times T is 15 plus 8 times 5 equal 100. 4 times 15 is going to be 60. And 4, hey. Now, just for kicks and giggles, let's see if 14, 6, or 614. Does 614 work? So 4 times 14 plus 8 times 6 equal 100. So that is 1656. 6 times 8 is 48. Yes, good. That gives us 104 does not equal 100. So it is, yes, it would work for the blue equation, but not for the green. not for green. So the answer is going to be 15.5. So let's get specific. And 5 is multiple choice. So there were 5 multiple choice and 15 true and false. That's a good problem. Hopefully you took the time to do that one, because that would be worth your time and effort. All right, you and your friends start biking from different locations on a 24-mile biking trail. Your friend starts at the trailhead and bikes 12 miles per hour. You start 1.5 miles from the trailhead and bike 10.5 miles per hour. After how many hours do you and your friend reach the same location on the trail? So we have this trail. And that trail is 24 miles long. And you start 1.5 miles from the trailhead and bike. So you are going to start, that distance is technically 24 minus 1.5. So that's how much. All right, we're figuring this out. Your friend, so friend is going to start at the trailhead. And you are going to start, here we go. So we don't want to do it to 24. You want to do it to your friend's distance. This is going to be your distance, right? So distance equals rate times time. We know that time's going to be the same because they start at the same time. It's just they're traveling at a different rate. So you start, you're going 10 miles per hour. Let's do your friend's distance is going to be 12 miles per hour times the same time. But they have a little bit more distance to travel than you. So your distance, when are your distances the same? When are you going to be the same away from each other? Yeah, I don't think that. So you get a 1.5. So your distance plus 1.5 should be equal to your friend's distance, which is 12t. I think that's it. Let's minus 10t minus 10t. We get 1.5 equals 2t. Divide by 2, divide by 2. We get 15 over 20 equals t, or 3/4. So time is 45 minutes. After 45 minutes, you, 45 minutes or 0.75 of an hour, or 3/4 of an hour. Yeah, that's good. That's correct. After how many hours do you and your friend? When are your distances the same? So I have to just add the 1.5 distance in order to, when are our distances the same? So this is 1.5 plus my distance should equal my friend's distance. That was good. You and your friend start. Who will reach the end of the trail first? How much longer will it take the other person to reach the end of the trail? Well, we know the distance is 24. So you, I'm only going, so I'm traveling at, so again, we have distance equals rate times time. My distance is going to be shorter than his distance, than my friend's distance. I'm only going to have to travel 22.5 at a speed of 10 miles per hour. So divide by 10, divide by 10, and we get 2.25 hours to travel. That's how long it takes me. My friend is also going to travel distance equals rate times time, but he has to travel all 24 miles, but he's traveling a little bit faster, so it only takes him 2 hours to do that distance. So even though I have a head start, he's going to beat me. My friend's going to beat me, and he's going to beat me by 15 minutes. 15 minutes. How many minutes did I say? 45 minutes, right? Yeah, 3/4. I just want to make sure I converted that correctly. Yeah, so my friend gets there first. What did we say? End of the trail, reaches the end. The end first, and he beats me by 0.25 hours, which is 1/4 of an hour, which is 15 minutes. Good. Those are good problems. If you want to test out of Algebra 1, you're going to have to know how to do those.